Okay, assalamu alaikum everybody. Today we will continue on chapter 23. We introduced chapter 23 last lecture, and so today we will cover part of chapter 23, and if we have time towards the end of the lecture we might be able to do some problem solving from the previous chapter 22. Remember, tonight you have your homework is due at 11 p.m. okay, and I posted the homework for next week. All right, let me remind you what we have done so far. Okay, we determined that if you have a charge or a charge distribution, then it will establish an electric field. Okay, and we were able to determine the electric field due to a point charge. And so if we have a point charge, Q, okay, then we can determine the magnitude of the electric field is K, which is Coulomb's constant, times Q divided by the distance squared. So if we are at the point P at a distance R, we can determine the electric field due to a point charge. So if we have a number of point charges, we can also use the superposition principle, and we said E total, if you have a number of charges Q1, Q2, Q3 and so on, and you are interested at a certain point P, we said that the electric field is going to be E1 plus E2 plus E3. So you have to write them as a vector addition. You can determine the magnitude and direction of each vector, and you add the vector sum. Okay. During last lecture we said if you have a uniform body, a charged object, we can also use a similar method, and we said so if you have a uniform charge distribution, okay, so let's say we have a charge Q, all right, we said that we can determine, we can divide this into small elements, each one of them has a charge dq, and we can determine delta E, the electric field from this point, it's just equal K dq divided, let me write it in magnitude form, divided by the distance squared, so r squared. So let's assume we are interested at a certain point P from this point, okay? And so if we add the contribution of all of these volume elements, dq1, dq2, dq3, we can get the total electric field is so the total electric field is actually the sum of all of the delta E's. This is a vector addition, okay, and this we can write it in a vector form, and we said that the electric field is the integral of K dq over r squared. And last time we did the derivation for a line charge, and we did the derivation for a ring, and we did also a derivation for a disk. Okay, so we used the integral form, this integral form, in order to determine the electric field from a uniform charge distribution. Okay, today we are going to try to simplify this a little bit further, because we know when you have integral equation, if you don't have a uniform or an easy geometry, it's not easy to do the integration. You have to use a computer and numerical methods in order to do that. Okay, so computers are very good. You can do a summation of the whole volume of all of the electric fields, and but if you do it manually, it's quite tedious. Today we're going to find another method which is quite powerful in order to determine the electric field due to a symmetric charge distribution. Okay, before I do that, let me remind you about the dot product, or the vector product of two vectors. Remember, in physics 121 and probably in calculus also you studied, if you have two vectors A and B and an angle theta between them, then A dot B, this is equal to the magnitude of vector A, the magnitude of vector B times cosine the angle between them. So the A dot B gives you a scalar, so this is a scalar. That's why it's called the scalar product, or the dot product. Okay, so if we have vector A and B are perpendicular to each other, theta is 90 degrees, cosine 90 is 0. So in that case, A dot B is equal to 0. This is actually a way of determining if two vectors are perpendicular to each other. You do the dot product. If the dot product is 0, then you know the vectors are perpendicular, or vice versa. If the vectors are perpendicular, you will always get a dot product between them that is equal to 0. If the vectors are parallel to each other, then, for example, here they are parallel in the same direction, A and B. So the angle theta is 0, cosine 0 is 1. So A dot B in this case is AB times cosine 0, which is 1. So you get, this is just AB. Okay. Now let me add another situation. If A is like this and B is in the opposite direction, okay, so the angle is 180 degrees. My pen is misbehaving today, but it's okay. So in this case, if you do A dot B, A dotted with B, it's going to be A, B, cosine 180, cosine 180, so this is minus A times B. Okay, cosine 180 is minus 1. All right? So this is going to be useful when for the next definitions. All right, let me go to the presentation mode. Okay. Yes, before I move on, if you have vector A and B in unit vector notation, for example, A is xi plus yj, and vector B is also in unit vector notation, it's ai plus bj, then the dot product, you take the product of the x components plus the product of the y component, and even if you have a third dimension, you can also add the product of the z components. So this will give you x times A plus 0, because I dotted with j is 0, j dotted with I is 0, plus y times b. So actually the easiest way to do the dot product is to write your vectors in unit vector notation, and just multiply the x components together, the y components together, and add. So this is an easy way of determining the dot product. Okay, let me define an area vector. Let's assume we have a closed surface. In this chapter we will speak about closed surfaces, and we will call them Gaussian surfaces, and you will see why we call them Gaussian, because Friedrich Gauss used these surfaces in order to determine the electric field due to uniform charge distribution. So let's assume we have a closed surface, and we call it the Gaussian surface. Okay, we define the area vector delta A, area vector. It has a magnitude and direction. So this is how we symbolize it, delta A. And so if we have an area dA, this is the vector, the area vector delta A. Its magnitude is just the area of the small surface on the Gaussian, so it's equal to dA. And the direction is always pointing outward, and it's normal to the surface. So the area vector, if you have a Gaussian surface, is always pointing outside the surface, and it's always perpendicular to the surface wherever you are. If you have a non-uniform shape, at any point the area vector has to be perpendicular to the area at that location. Okay, the magnitude is obviously the area of the small surface on the Gaussian. Okay, all right, so let's now define the flux. The total number of lines penetrating the surface delta A is proportional to the product E times delta A. Remember when we used electric field lines, we said the number of electric field lines are proportional to the magnitude of the electric field. Okay, the product of the area, the delta A and E, is called electric flux. So this is a definition. This product of the magnitude of the electric field and the surface area perpendicular to the field is called the electric flux. So notice this is it has to be perpendicular to the field. That's why in order to use only the perpendicular component, we define the electric flux through an area delta A as E. This is the electric field vector at that location, dotted. This is a dot product with the area, the area vector delta A. Okay, so we can write that this is the definition of the flux at this location. So for this area delta A. Okay, now we know the dot product of two vectors is the magnitude, the multiplication of the magnitude of the two vectors times cosine the angle between them. So if we know the angle between the electric field and the area vector, so let me symbolize them as vectors, okay, then we can determine the flux is just E times delta A times cosine theta. The unit of the flux is, the unit of the electric field is newtons per coulomb, and the unit of the area is meter squared, so the unit of the flux is Newton meter squared per coulomb. Newtons meter squared per coulomb. Okay, why are we defining the flux? You will see it will come in very handy when we speak about Gauss's law. Okay, now let's assume you have a large area. If you have a large area, you can divide it into small elements, delta A's, okay? Determine the area vector on each of these elements, and you can determine the flux through this area by adding the fluxes through every elemental area dA. Okay, so we can write the total flux through an area is just equal to the summation of E dotted with dA. Okay, or we so in this case, if the angle does not change between the electric field and the area vectors, then no problem. But if this area is not a flat area and the angle changes, then you have to determine what is the orientation of the area vector, or what is the angle between the electric field and the area vector at each location. Okay. All right. Now, if we make these elements, the area elements, very small, if we make delta A approach 0, this Riemann sum becomes an integration. So it becomes an integral equation. So we can write that the total flux through the area in this case is the integral. It's the integral of E dotted with dA. So here it's just the summation becoming an integral when the element area dA becomes quite small. All right. So this is the definition. So you give me a shape. I can do this integral if I can. If it's not difficult geometry, if it's a uniform geometry, you will see it's quite easy to do this integral. Okay. All right. So all right. So let's take some situations for the flux. Let's assume, for example, we have this is the area delta A. This is the area vector. This is the electric field vector. Now they are parallel to each other. So if you do the flux in this case, it's just E dotted with delta A. The angle cosine theta, cosine of 0 is 1. So the flux in this case is just equal to the electric field magnitude times the area delta A. Let's take another situation. So let's assume, for example, here the electric field is tangential to the surface or parallel to the surface. Hence, it's perpendicular to the area vector, because the area vector is always perpendicular to the surface. Okay. So if you do the flux in this case, what is the angle? The angle between the area vector and the electric field is 90 degrees. Cosine of 90 is 0. So in this case, the flux through this area is going to be 0. So if the electric field is tangential to the surface, parallel to the surface, then the flux of the electric field through that location is 0. Last case, let's assume, for example, the angle is 45 degrees between the area vector and the electric field. Remember, the area vector is always perpendicular to the surface, so this is always perpendicular to the surface. Okay, so in this case, you just do the flux E dotted with the A. It's E delta A times cosine 45 degrees. Okay, clear? So the flux is just the E dotted with delta A, and so if you you have to determine the angle, and you will see in many situations it's relatively easy to do this. So the electric flux through a surface is maximum when the electric field and the area vector are parallel. You can see this. This is the maximum it can get. Okay. The flux is 0 when the electric field and the area vectors are perpendicular to each other. Okay. And if the electric field and the area vector are 180 degrees away apart, then the flux will be minimum. It's negative number. It will be minus EA. Yeah? Okay. So we have defined the flux. All right. So let's take, for example, now a closed surface, and we want to determine the flux through a closed surface. We can use the same technique as we did earlier. Okay. So we divide it into small elements, delta A's. We can determine. We can determine the flux through each of these elements. So it's just E, the electric field vector at that location, dotted with the area vector, delta A. Okay, so we can write it's equal to the magnitude of the electric field times delta A, which is the magnitude of or the area of this small element, times cosine of the angle theta. Now, if we want to do the total flux through the closed surface, we sum all of these fluxes, all of these elemental fluxes, okay? And if the area becomes very small, this summation becomes an integration. So again, so this is the Riemann sum. So we sum all of the fluxes through all of the areas of this closed surface. We can get the total flux through this. And if the area becomes quite small, in this case, we can write that the flux is equal to the integral of E dotted dA. So here, this is not a closed surface, but if it's closed surface, we use a different symbol. If it's a closed surface, for a closed surface, so let's assume this is closed surface, we write it the following way. The flux is the integral, and so we do this circle on the integral to indicate this is a closed surface, and it's the same equation, E dotted with dA. And this is what we are doing next. So here is a heart. So you can see this is a closed area, and you can see the electric field lines going through this heart. So at a certain point they are going into the heart, at some other point they are going out of the heart, and at some point they are skimming, they are tangential to the heart. So you can see for this point here, the electric field is piercing into the closed area, and so the angle theta is more than 90 degrees in this case. So the cosine of theta is negative. At this location here, you can see that the angle between the electric field and the area vector is less than 90 degrees. So cosine of theta is going to be positive in this case. Okay, and if the electric field, like in this location here, it's just tangential to the surface, so the area vector is perpendicular to the electric field, and we said if they are perpendicular, the flux will be 0. All right, so this is okay. So always draw the area vector pointing away from the surface, from the inside, and perpendicular to the surface. So if the electric field pierces outward, like here, if it pierces outward, okay, then the area vector makes an angle theta, usually between 0 and 90 degrees. So cosine theta is positive. Thus, the product of EDA, which is the flux at that location, is positive. Okay. Now, if the electric field pierces inward, like here, okay, so in this case, the angle theta is going to be between 90 and 180 degrees, as you can see, the angle. And so cosine theta is going to be negative, and E dotted with dA, which is the flux at that location, is going to be negative. So if the electric field skims or is tangential to the surface, then the area vector and the electric field are perpendicular. The angle is 90 degrees, cosine 90 is 0, so the flux at that location is 0. Okay, so now we have some clear ideas how we can determine. So the general rule for an inward piercing electric field, theta larger than 90, the flux is negative. For an outward piercing field, the angle theta is less than 90 and higher than 0, the flux is positive. And for a skimming electric field, meaning it's tangential to the surface, in that case the flux is 0. واضح? Clear? Okay. So let's take an example. So here we have an electric field, is uniform electric field, so it's same direction, same magnitude everywhere. It's going through a closed surface. This closed surface is a cylinder, okay? And we want to determine what is the flux through this closed surface. So since we have a cylinder, we can divide it into 3 areas. Area number 1, in this case the electric field is piercing through this area. Area number 2, which is the belt of the cylinder, this is area number 2. So this is what we call 2. And you can see the electric field in that case is perpendicular to the area vector. You can see the area vector, it's an angle of 90 degrees. And the third area is actually the area to the right, for which the electric field now is piercing out. So the angle between the area vector and the electric field is 0, and the flux is positive. So what we can do, we can write this subdivided into 3 integrals for each of these areas. So we'll do the integral for area 1 plus the integral for area 2 plus the integral for area 3. You can already see for area 2 it's going to be 0 because the electric field and the area vector are perpendicular. You see here there is an angle of 90 degrees, so this will be 0. Okay. Now for this area here, notice the angle, area number 1, the angle is 180 degrees. So cosine 180 is minus 1. So we expect that this will be E times the area. So let me call it dA minus, because cosine of 180 degrees is minus 1. Okay. And for the last one, we have E and the area vector dA are parallel to each other. The angle theta is 0. So E dot dA is equal to E dA cosine of 0, which is 1. So we will get this is going to be plus E times dA. So this will be the total flux, right? So here, so we replace the angles, okay? E dA cosine 180 for area number 1, E cosine 90 dA for area number 2, cosine 90 is 0, and for area number 3 it's E cosine 0. Okay, so in this case, so this is minus E times A, so we call this area A. So let me yeah, so all right. And the integral through the belt is 0. The integral through the right surface is just EA. And notice that minus EA cancels with EA, and we get a total flux of 0. A total flux of 0. And actually, we can generalize this, and you can take it as a rule for any closed surface, that is placed in a uniform electric field. The total flux will be 0. You can verify the electric field lines moving in are cancelled with the electric field lines moving out. So the number of electric field line moving into this closed surface and moving out, they cancel each other. The total flux is 0. Okay? So, but I underline this is in a case of a uniform electric field. But we will see, we will use a more general rule later on to generalize it. Now, for a closed surface that does not enclose any charge, the total flux is 0. We will verify this later. So if there are no charges inside any closed surface, the flux through that surface is 0. We are actually touching on Gauss's law now. Okay, so for a closed surface that encloses a net positive charge, so if you have a closed surface but you have a net positive charge inside it, the flux is going to be positive. It's outward, it's going to be positive. And for a closed surface in which the enclosed charge is negative, the flux is going to be inward. It's going to be negative. All right, so these are general rules, and we will verify them. All right, so let me start the Kahoot on this one, and show. Start. No. Sorry. Okay, so we will play this one. Please, everybody enter the Kahoot because I use it for attendance. Okay, so this is the pin number. It will show. Interesting, the sound is not really coming out. Okay, yeah, the sound is not working. It's okay, we don't need it. All right, so enter the pin number 673-6374. Okay, this is the question. Okay, please everybody enter the Kahoot because I use it for attendance. Don't use your name. I have at least 4 al-Anud, so if you put al-Anud or I get confused. Please use your ID number, and after your ID number you can put your name. Okay, so let me start. So read the question and enter your. I will give you a chance to enter your answer A, B, C, or D. Okay, made up your mind? Okay, so let me start the Kahoot, and you will have 20 seconds to choose between A, the flux increases. If you have the radius, the flux increases, or the flux decreases. B, the flux remains the same, or D, the flux becomes 0. Next. Ten seconds. Two seconds. All right. Okay, so we have 9 who think that the flux in this case does not change, but the majority, they are saying that 21, they are saying it changes. It either 0 becomes 0, or increases or decreases. All right. All right, so this is a little bit unfair question. Okay, and all right, so let me go here. So let's assume we have a charge Q, and we know if your charge is positive, the electric field lines are going to be pointing outward. The electric field is actually pointing away at each of these locations, the electric field at each of these locations. Okay? And I want to determine the flux at this radius R. So let's assume I make a sphere of radius R around this charge, and I'm going to try to determine what is the flux. And then I will determine whether the flux, if the radius increases or decreases, whether it changes or it does not change. All right, so let's write the flux. The flux, we said, is E dotted with the A. Okay. All right, so let's do this. Notice that at any location on the sphere, the area vector is perpendicular to the surface. So this is the area vector here, delta A. This is the area vector here, delta A, and so on. So notice that in this case, delta A is always parallel to the electric field. So the angle between them is 0. Okay, so I can write that this is actually equal to E times cosine of 0, which is 1. Cosine of 0 is 1 times dA. Okay? So, what is the electric field at a distance r from a point charge? We already know that. We know from Coulomb's law that the electric field, from Coulomb's law, we know that the electric field is just kq divided by r squared. Okay? So, I can write that the flux now is going to be equal. So, let me do the integral. Okay? So, kq divided by r squared, the closed area dA. Okay, what is this integral? The integral over the whole sphere for each of the elements dA. It's actually the area of the whole sphere, isn't it? So you're doing the integral over the whole sphere, and you're adding all of these elements, so you end up with the area of the whole sphere. Okay, what's the area of a sphere? 4 pi r squared. So the flux is kq divided by r squared times 4 pi r squared. So this is the area of the sphere. So this is the area of sphere. Notice what happens. What happens to the dependence on r? It cancels. The r squared will cancel, and we end up with a flux that is equal to 4 pi. Okay, 4 pi times k. Remember, k is 1 over 4 pi epsilon 0. Correct? Okay, so, and times q. So the 4 pi's will cancel, and we end up with the flux is just equal to the charge q divided by epsilon 0. Quite interesting result. It does not depend on the radius. So if you halve the radius, or you double the radius, or you multiply it by 100 times, the charge enclosed is still the same. Q is the same. So this does not depend on R. Very interesting result. Gauss, when he observed this, he generalized this rule. He said, any closed surface, okay, the flux through that closed surface is just equal to the charge inside it divided by epsilon 0. So actually, we just have derived Gauss's law for a single charge, or for a point charge. But this law, we will see later on, is actually valid for any situation. Actually, any closed surface, the flux through that closed surface is just equal to the charge enclosed by that surface divided by epsilon 0. It does not depend on the radius, does not depend on the shape of the surface. Very interesting result. Okay, so this answers this question. So here the flux remains the same, because we determined that the flux from a charge is just equal q divided by epsilon 0. You halve or you double the radius, the flux will still be the same. Okay, so let's do one more example of the flux before we introduce Gauss's law. Okay, so here we have a uniform electric field E. This is the uniform electric field here. So it's piercing through the back surface and is coming out of the front surface. Okay, oriented in the x direction. So it is in the x direction in empty space. A cube of length L, okay, is placed in the field. So this is the cube of length L, oriented as shown in the figure. Find the net flux through the surface of the cube. All right, so we will just use the definition. We said the flux is the integral. So in this case, it's E dotted with dA. Okay. To simplify things, I can divide this into 6 surfaces, because clearly I have on a cube we have 6 surfaces. So let me call this area here 1, this back area 1. Okay, the front area I will call it 2. Okay, and the side areas I will call them 3, 4, 5, and 6. Okay, so this flux here is going to be the integral over E dotted dA with area 1 plus the integral of E, okay, let me use the vector notation, E dotted with dA for area 2 plus, so we will continue this until we reach for area number 6, E dotted with dA. Okay, so first of all, notice that for areas 3, let's take for example area 3. Area 3, the electric field is like this, so it's tangential to the surface. It's perpendicular to the area vector. There is an angle of 90 degrees. So clearly, E dotted with dA3 is equal to 0. Same thing if you go to the bottom, area number 4. So E dotted with dA4 is also 0. Same thing on the sides. If you come to the side here, the area vector is pointing in the Z direction. So let's draw this one here. So the area vector is pointing in the Z direction. dA, what do you call it? 4. Okay. The electric field is tangential to the surface, so they are perpendicular. So the same thing, E dotted with dA4 is 0, and E dotted with the area that is on the other side, which is 6, E dotted with dA6, because the electric field is perpendicular to all of these surfaces, is also equal to 0. So what we are left only with area number 1. Okay, so for area number 1, notice the electric field makes an angle of 180 degrees. This is the electric field here, so it makes an angle of 180 degrees. So the flux is going to be, for area 1, is going to be E times cosine 180 dA. This is for area number 1. For area number 2, which is the front surface, notice the electric field now is parallel to dA2. The angle between them is 0. So plus the integral for 2 is E cosine 0 is 1. Cosine 0 is 1 times dA. So this is actually minus E times the area of the surface, which is L squared. The area of the surface is L squared. Okay. The front area is also L squared plus EL squared. So it's equal to 0. The total flux, like the previous case where we had a cylinder, back surface, front surface, and a belt, we said a closed surface, if you do the flux through a closed surface in a uniform electric field, it will give you 0 flux. This is very similar. This is an electric field that is uniform, same direction, same magnitude, and we're putting a closed surface inside it that does not enclose any charge, so the flux will be 0. We verified that the flux now through this cube, the total flux is 0. Okay, so now let us go to Gauss's law. We just have proven Gauss's law for a point charge. We determined that if we have a point charge, the flux around that point charge is just equal to the charge enclosed divided by epsilon 0. Very surprising. Nobody expected this at the time of Gauss. He lived in the early 1800s. He was a German physicist and mathematician, and he came up with this rule. He said the net flux through any closed surface surrounding a point charge Q is given by Q divided by epsilon 0 and is independent of the shape of the surface. This is the genius. Well, we have shown it for a point charge where the surface is spherical. If you like math, try to prove it for any shape. If you can prove it to me and bring me the derivation, this is a challenge, you will get a bonus point that will count significantly. If you can prove this Gauss's law, not for a spherical, or prove it for any surface, mathematical proof. It's not simple. Okay, so this is a general rule. The flux through any closed surface, this is the definition of the flux. is just equal to the charge enclosed by that surface divided by epsilon 0. It simplifies our lives. So if you give me a closed surface, if you tell me what's the charge inside it, I can tell you what is the flux. Or vice versa. If you give me a closed surface and you give me the flux through the closed surface, I can tell you what's the charge inside it. It's like magic. So yes. Doesn't have to be spherical. The surface can be any shape. That's the challenge. That's the challenge. Yes. No. We said, I did not say the flux through any closed surface is 0. I said if you put a closed surface in a uniform electric field, the flux will be 0. So the other way to say this, if there is a charge inside this closed surface, if there is a net charge inside of this closed surface, the flux will not be 0. This is what Gauss's law says. It depends on what the charge is enclosed by this closed surface. If the charge enclosed by this this is more general than the rule I told you earlier. The rule I told you earlier, if you put a closed surface in a uniform electric field, it has a 0 flux. And through that closed surface. This is even more general. This is saying any closed surface, the flux through this closed surface is equal to the charge enclosed by the surface divided by epsilon 0. So if the net charge enclosed by any closed surface is 0, then the flux is 0. This is much more powerful, much more general than the law I said earlier. Okay, so let's for example take the charge again from before. So this is a point charge. We did it for a spherical surface. Let's now make it a non-spherical, but it's an irregular shape. Okay, we notice in this case that the flux is proportional to the number of the electric field lines passing through the surface. So the number of electric field lines passing through S2 is the same as the number of electric field lines passing through S1. Okay, and hence the net flux through S2 is going to be equal to the flux through S1. This is hand waving. This is not a mathematical proof, but I want you, if you can, prove to me this. Can you prove this mathematically? Okay, so any irregular shape, closed surface, the flux through it is going to be just equal to the charge enclosed by that surface divided by epsilon 0. Not only that, let's take this is another closed surface. So this is a closed surface that does not have a net charge enclosed. There is a charge close to it. There is a charge close to it. If you look at the flux through this closed surface, one way of looking at this, looking at the number of electric field lines moving in minus the number of electric field lines moving out. Notice, let's see, 1, 2, 3, 4, 5. 5 electric field lines moving into this closed surface, and 1, 2, 3, 4, 5, and 5 electric field lines moving out of this closed surface. So the number of lines moving in is equal to the number of lines moving out, meaning the flux is equal to 0. So you can see here, this is a closed surface. The electric field is not uniform in this case. Notice the electric field, it changes direction, and it increases with magnitude as you get closer to the charge. So it's not a uniform electric field. This is a closed surface in a non-uniform electric field, yet the flux is 0. Why? Because there is no charge enclosed by this closed surface. This is the power of Gauss's law. Any closed surface, you tell me what's the net charge enclosed by the surface, I can tell you what's the flux. Flux is just equal to the net charge enclosed divided by epsilon 0. Okay, let's see if you understand what I'm saying or not. Okay, so let me go to presentation mode. Okay, so I'm taking longer than I expected, but it's okay. This is very important concept to spend time on. Okay, what is the flux through surface S1? You see here we have the charge Q on the top, charge minus Q on the bottom, and I have different surfaces. What is the flux through S1? Now, what is it? I know it's positive, but what is it equal to? Q over epsilon 0, period. Okay, so in this case, simple, the flux is just equal to the charge enclosed, which is Q divided by epsilon 0. Very easy, even though it's an irregular shape. Now, also the flux you said is positive. It is positive because the charge is positive. What is the flux through S2? Yes? Somebody raise your voice. Yes? Minus Q divided by epsilon 0. We said it's the charge enclosed. In this case, the charge enclosed by S2 is minus Q divided by epsilon 0. I have to do duplicate so that the other students can see recording. Okay? So the flux in this case is minus Q. The charge enclosed is minus Q divided by epsilon 0. And notice in this case, because the charge is negative, the electric field lines are all moving into surface S2, so it's a negative flux in this case. Okay? How about, what is the flux through S3? You can see S3, 0. Immediately, you say S3 does not have a net charge enclosed inside it, so the flux through it is going to be 0. Notice in this case, it's not a uniform electric field. The electric field is actually changing direction. You can see the direction of the electric field here is like this, and here it's like this. So this is not a uniform electric field, yet the flux is 0 because there is no charge enclosed in this surface. Last question. Okay. What is the flux through S4? You know S4 is the total surface here. What is the flux through S4? 0. Why? Because the charge enclosed is Q and minus Q. Q minus Q is 0, so the flux is 0. واضح? So I give you any drawing with and put the charges, you should be easily just the charge enclosed divided by epsilon 0, you get the flux. Okay, so the net charge inside the Gaussian surface is 0. If the net charge inside the Gaussian surface is 0, the net flux through the surface is also 0. Basically Gauss's law. Okay, now we're going to try to derive Coulomb's law from Gauss's law for a point charge, and let's keep things simple. So we said this is a charge Q. Okay, so let's write Coulomb's law. The flux, which is E dotted with dA, is equal to the charge enclosed divided by epsilon 0. Okay, so let's draw a Gaussian surface. Let's put a radius r here. I'm going to use it for this Gaussian surface. Now we know from the symmetry of the problem, the electric field is always pointing away from the positive charge, so there is a symmetry. And if I know the area vector is also always pointing away from this the inside of the surface, and is perpendicular. So you notice that the electric field is always parallel to the area vector dA, meaning E dotted with dA. I can simplify this. So this is E dotted with dA, so it's going to be cosine 0. Cosine 0. The pen is misbehaving. Cosine 0 dA. Okay, this is equal to the charge enclosed, which is Q divided by epsilon 0. Okay, now cosine 0 is 1, so this becomes the integral E dA, which is a charge enclosed divided by epsilon 0. Okay, from the symmetry of the problem, since all of these points are at the same distance, so the electric field is going to be the same strength. Okay, so I can take the electric field outside the integral, and becomes E, the integral dA is equal to the charge Q divided by epsilon 0. What is the area of the sphere? 4 pi r squared. So this integral of the closed integral, if we add all of these area elements here, it will give me the area of the sphere. So this becomes, the flux is going to be E times 4 pi r squared, that's the area of the sphere, is equal to the charge enclosed divided by epsilon 0. So what's the electric field? The electric field is 1 over 4 pi epsilon 0 Q divided by R squared. What is this? It's Coulomb's law. So it's equal K Q divided by R squared. This is Coulomb's law. Notice earlier we used Coulomb's law to derive Gauss's law. So we started with Coulomb's law and we reached that the electric field is equal to the charge, the flux is equal to the charge enclosed divided by epsilon 0. So we started with Coulomb's law and we derived Gauss's law. Here we did the opposite. We started Gauss's law. This is Gauss's law. And we derived Coulomb's law for a point charge. It's easy to do, because it's symmetric and it's a sphere. If you want to do it for a more complex geometry, you're welcome. It's more challenging. Okay. So this is what we just have done. So let me skip through this. So we started Gauss's law and we were able to derive Coulomb's law. So if you remember one, you can derive the other one. Gauss's law is useful, very useful, in determining the electric field when you have a symmetric geometry. Okay, so this is what we're going to do next. So now we used Gauss's law to determine the electric field for a point charge. We're going to try to do the same thing for uniform geometries, because this is very powerful. It's much easier than the previous one. Okay. All right. Well, let me skip through this one because it's not difficult. It's easy. Let me do this one very quickly. Okay. So here I have a geometry where I have different charges Q1, Q2, Q3, Q4, Q5, and I have a surface S. What is the net electric flux through the Gaussian surface S? I just use Gauss's law. The flux is equal to the charge enclosed divided by epsilon 0. The charge enclosed in this case by the surface S is Q1 plus Q2 plus Q3 divided by epsilon 0. So notice Q1 is 3.1 nanocoulomb, Q2 is minus 5.9 nanocoulomb, and Q3 is minus 3.1 nanocoulomb. So you add them, scalar addition, you divide by epsilon 0, you will find the flux. So very simple. So you find that in this case, the flux or the net flux through the Gaussian surface in this case is minus 670 coulombs per Newton per meter squared. Okay. Now I want to go to Kahoot for this one because this is a critical one. Discard, and let me go to the Kahoot for this one. Okay. So next, yes. So read the question and answer it. You have three options: A, B, and C. Ready? Okay. So I'll start the Kahoot. Ten seconds. Excellent. 20 are correct. This is the highest correct answers we had so far. All right. So, but we still have 7. What was the distractor? So let's see. The distractor was there are no charges inside the surface. Remember, S4 had a charge Q and has charge minus Q, so it has charges. It's just the net charge. If the net charge is 0, the flux is 0. So you cannot say if there are no charges. No, you can have charges. Like the case where we had the S4 here. Remember, for the S4, are there charges inside? Yes, there are charges, but the net charge is 0. Q minus Q is 0, so the net flux or the flux through this closed surface is 0. So the correct answer in this one, and I know it's deceiving, it's the net charge inside the surface is 0, not there are no charges inside the surface. There can be charges, except they cancel each other. Okay? All right. So let me ask another question. All right. All right. So here we have a spherical Gaussian surface surrounded by a point charge Q. Okay. Describe what happens to the total flux through the surface if the charge is increased. If the charge is increased, what happens to the flux? Increases. The flux increases. So here, point charge Q. So yes, the flux, or let's say the magnitude of the flux increases, because if the charge is negative, if the charge is negative and its magnitude increases, becomes more negative, also the flux becomes more negative. What happens if the radius of the sphere is reduced? Does not change. We said it's the charge enclosed divided by epsilon 0. There is no dependence on R. What happens if the surface is changed to a cube? Does not change. It's still a closed surface. The charge inside it is still Q. The flux is still the same. It's Q divided by epsilon 0. What happens if the charge is moved to another location inside the surface? Does not change. So that means if I have a cube, it does not matter where the charge is. It's in the center or on the side. As long as it's inside the cube, the flux is going to be the charge enclosed, which is all, it's Q, divided by epsilon 0. So it doesn't matter. I can move the charge inside my surface. I still get the same flux. So these are very important observations. Okay. Well, I want to really solve some problems from chapter 22. So let me stop this and go to chapter 22 and do some problems. And so let me end this one. Let me start the other Kahoot. I know I can do that. Okay, so let's go to chapter 20. Let's see, chapter 22, and there is station 2. Okay, so exit from that Kahoot, and you're going to start another Kahoot. So exit the Kahoot that you are in, and we're going to start a new one. So this will be the pin. So 718-2084. Okay, 718-2084. So I will start to save some time. Okay, so please everybody play with us. Okay, so 2 minutes for this question. This is an easy question we did in class. 2 minutes for this question. Okay, even for the students who I'm recording this for, please take the time to solve the problem. Don't just keep watching. Just solve the problem as if you are in class with us. Everybody, please. Practice is very important. Ready? You should be ready. We did this before. So I will give you another 20 seconds. So choose between A, B, C, or D. I'll start. Five seconds remaining. Okay, 13 correct answers and 15 incorrect answers. Still, some students are not participating, but it's okay. All right, so let's see. This one is here. Okay, so here we have a small ball of mass m, 5 10 to the minus 3 kilograms. Okay, and a charge of 4 microcoulombs. What is the magnitude of the electric field directed upward when will balance the weight of the ball so that the ball is suspended motionless over the ground? So this is the ball. Okay, this is an equilibrium problem. We draw the forces. We have a force mg, a gravitational force, and in order for it to be balanced, it has the electrostatic force has to be pointing up. So this is equal to QE. Okay, so the analysis of the problem, we have equilibrium. Sum of the forces is equal to 0. So we have only forces in the y direction. So in this case, we can write just Fe is equal to mg, which is QE is equal to mg. And we can get the electric field is just equal to mg divided by q. And when you calculate this, you find that this is 1.22 10 to the power 4 newtons per coulomb. Okay, next problem. So 59402 is leading, he or she is leading. Okay, all right, so 2 minutes for this one, 3 minutes for this one. تحب نكبر يعني let me bring it here, let me see it. Okay, so here, okay, you can see it now. Okay, so I will give you 2 minutes, 2 or 3 minutes, yeah, 2.5 minutes, 2.5 minutes, let's be generous. Students watching a video, please also do this practice. One minute left. Okay, so let me go back to the other one. Okay, so you have choices between A, B, C, and D. Okay, I will start the Kahoot. So choose between A, B, C, or D. You have 20 seconds to enter your answers. Okay, 18 correct answers, and we have 11 incorrect answers. Did you see the answer from the previous slide? Huh? Okay, it was there, but it's okay. I think most of you would got it right. Huh? So let's look at this problem. What's the problem? Okay, all right. So here, 4 particles are fixed in places and have charges Q1 equal Q2 is equal to 5e. These are positive charges. Okay, Q3 is 3e, positive charge, and Q4 is minus 12e, negative charge. Distance D is 5 micrometers. What is the magnitude of the net electric field at point P due to the particles? Okay, so actually from this geometry I can choose my x and y axis to make things simple. All right, and I can choose them to be like this. This is my x-axis, and I can choose my y-axis. All right, now I'm going to draw the electric field at point P from each of these charges. So let's start with Q1. Q1 is positive, so the electric field pointing away from it. So let me write, this is E1, and E1 is KQ1 divided by the distance squared. All right, how about Q2? Q2 causes an electric field also pointing away from it. So this is E2. And notice E2 has the same magnitude but opposite direction. So KQ2, which is equal to Q1 divided by D squared. So we can see already that E1 and E2 will cancel. So I can write E1 plus E2 vectors will give you me 0. So I don't have to worry about them. Okay, how about Q3 and Q4? So let me draw. Q3 is positive, so the electric field is like this. It's pointing away from the point charge. So this is E3. Okay, so let me write E3. E3 magnitude is K Q3 divided by the distance, which is D squared. Okay, how about Q4? Q4 is a negative charge. The electric field is pointing towards it. So the electric field E4 is like this, E4. Okay, it's in the opposite direction, it's positive x direction. So E4, I can write the magnitude is K. So let me use the absolute value of Q4 divided by the distance. Notice the distance now is 2D, it's not D. The distance is 2D, so it's 2D squared. Okay, so let's evaluate. E3 is K, Q3 is 3E divided by D squared. This is E3 magnitude. The magnitude of E4 is K. Q4 is 12E. If you take the absolute value, 12E divided by 4D squared. So this is actually 3KE divided by D squared. Notice the magnitude of E3 is equal to the magnitude of E4. And they are pointing in opposite direction, so they cancel each other. So we can write also E3 plus E4 is equal to 0, because one is pointing the negative x direction and the other one is in positive x direction, and hence E total is equal to 0. Okay, many problems you find that the electric field, do not have to solve every one of them. First of all, draw the electric field vectors, see which ones cancel. In many problems you'll find the number of electric fields cancel each other. So you only have to evaluate for the ones that do not cancel, and it makes your life easier. Okay, let's do one more problem. I think we have time. Next, let me skip this one. We did a similar one in class. Skip. Next. Yes, let's do this one. Okay, and I'll give you 2.5 minutes for this one. Can you see it? Please, next time come closer, because you want me to read it? An electron with a speed of 3 × 10⁶ meters per second moves into uniform electric field of magnitude 1 × 10⁻³ newtons per coulomb. The field lines are parallel to the electron velocity and pointing in the same direction as the velocity. How far does the electron travel before it is brought to rest? How far does it travel before it's brought to rest? Nice problem. Please try to do it. This is a very important problem. It combines 3 important concepts in physics. It's the struggle and the thinking that will establish the connections between the brain cells. Remember? The harder you think, the better you become at solving problems. Okay, so let me start the Kahoot. لا خلاص. I want to have time to solve it also. Sorry about that. I have only 2 minutes left, and I don't want to keep you after class. So okay, so wow, impressive. We have 12 correct answers. Okay, that's impressive. Okay, so let's go to this problem. All right, so this is the problem here. The electron has always in problems like this, I like to draw the situation. So the electron is moving with the velocity v, 3 × 10⁶ meters per second, okay, into uniform electric field of magnitude of 1 × 10⁻³ newtons per coulomb. Okay, the field lines are parallel to the electron's velocity and pointing in the same direction. So the electric field is in this direction. This is the electric field. Okay, now where do you think the force is in this case? Is it in the positive direction? This is the x-axis. Is it in the positive x-axis or in the negative x-axis? Negative, because it's a negative charge. So the force is going to be, let me change the colors. The force is going to be like this, Fe. This is a constant force. So we're going to use, first of all, the force. The magnitude of the force is Q times E, so I'm going to just use the magnitudes. So I will take the absolute value of Q. Okay. The next law I'm going to use is the force is equal to ma, Newton's second law. So this force, there are no other forces. This is equal to ma. Okay. So I can get the acceleration is constant. The magnitude of the acceleration is Q times E divided by m. Okay. What else I need to solve this problem? They are asking how far does the electron travel before it's brought to rest. Exactly. We use constants of motion, equations of motion at constant acceleration. And so we have 3 equations. We can use the third one, which is v² minus v0². okay, is equal to 2a times the distance traveled here. Okay, so here I will put minus sign because the v final is going to be 0, v initial, so v final is 0. Okay, that's why I have a minus sign, and I can solve for d. So d is going to be v initial squared divided by 2a. So this is v squared, v0 squared divided by 2a. And when you do this, you find the number is okay, so d is going to be equal to 2.56 centimeter. Okay, it's clear. So we used three concepts. Electrostatic force is equal to QE. The second concept, we use force is equal to MA. The third concept, we use equations of motion at constant acceleration. So this is a problem. It's a simple problem, but combines three important physics concepts. We'll see you tomorrow, inshallah. The quiz is on Thursday at the end of the class, between 12 and 12:15 in class. And it will be open-ended questions. No multiple choice.